Okay. So can everyone give a round of applause to Dr. Matt Himsworth?
Can everyone hear me? Yeah. Okay. What bingo words do we need to find now? I'll try and work.
Exciting and curious.
Exciting and curious. Well, that doesn't count. Okay. So we've had a talk from an astronomer and a theoretist. I'm an experimental physicist. I'm actually an atomic experimentalist theorist, so I'm more at home with spanners and lasers than I am with equations, I must say. And I'm going to, we talked about things in the dark that are above us, things in the dark that are too small to see. I'm going to talk about what's in between, something a bit more down to earth, and actually what's underneath the earth. Because we don't actually know most of what's underneath us. And it can affect our everyday lives. So we'll talk about kind of what's underneath us, how we find out what's underneath us, and some cool new technology. So I'm going to lull you into into a kind of a, what's it called? Some kind of confidence in kind of classical physics. We'll talk about mountains and volcanoes and things. You're happy with those. Then I'm going to hit you with a load of quantum mechanics right at the end. Okay, just so we need to Okay. So, I'm going to talk about the Earth, what's underneath us. The Earth is made of it's got a solid core, and around that solid core it's got a liquid mantle. The core's very hot. In fact, it's hotter than the surface of the sun. The centre of the Earth. That heat's kind of left over from the formation of the Earth and some radioactive decay and things like this. That's about 6,000 kilometres below us. Right. If we go a bit closer to the Earth, what happens is you've got this heat that's coming. Oh, no, don't do that. Where's the laser? Middle. Right. So you've got heat from the Earth. Sometimes that heat needs to be released. And it comes up through this kind of mantle where it causes convection currents, as you can see in your tea. It's mixing. Occasionally it comes up, pokes through that very thin crust near the surface, solidifies, and it forms new mountain ranges. And the crust on the surface, this really, really thin crust, only about 10 kilometres. So this is, so the centre of the core is from down here somewhere. This is kind of the mantle kind of area. The crust is just that tiny bit there, and that tiny thin bit is just the plates that we sit on top of the crust. It really exists in a very small amount. Anyway, it pushes up, we're on the Earth, and it pushes up and it kind of starts spreading out that thin crust on the top. And so what happens is all this is happening around the world, and all these crust is pushing against each other, and they break into little plates, plate tectonics. They push against each other, and you get this kind of crinkling of the crust, and that's mountain ranges and other volcanoes and things. Why does it affect us? Well, you don't want to be near a volcano, you don't want to really be in Hawaii at the moment, because of this thing happening. Also it causes earthquakes, and there's some scary stuff that give you nightmares. It's called supervolcanoes. Does anyone know what's on the Yellowstone National Park in America? It's one of these, that's a picture of what's, well, that's an image from data of what's underneath Yellowstone. Huge volcano. So if that thing erupts, you don't have to worry about global warming anymore. Okay, so let's zoom in on that. So, I'm going to stop doing this. There we go. Zoom in on that tiny crust just there and see what's there. Okay, so this is the kind of the bit area that we're interested in, that we want to look down. This is where all the oil and the gas and everything that we need, the minerals, the metals, the diamonds, to keep our kind of quality of life as we're going at the moment. So we kind of drill down here, collect and extract these minerals. The deepest hole we've ever gone down is the Kola super deep borehole. It goes down 12 kilometres. So that's, you know, this is only about a few kilometres on this screen here, so we're 12 kilometres down here. And that's still nothing compared to the kind of depth of the mountain. So we've got things like fresh water. There's water we can't get to. You know, areas where you've got drought, like California, if you can drill down to the water, it's very useful. If we want to be able to find where these oil reserves are, find where the mineral reserves are, because when we run out, we need more extra ones. So if we can look under the earth and find out where they are, that's really useful. Also, these things don't stay static over time. The water comes in here, it erodes things away, and you can get fun stuff like sinkholes opening up and happening more and more as the weather starts getting a bit weird and wonderful. And also things like mine shafts open up. So mine shafts are quite scary. Okay. And on the top of that, there's all the clutter that we stuck there. So all of our utilities, gas, electric, sewage, and you know things like come on. This is Bank Station, that's what it looks like underneath. kind of really complex mix of kind of pipes and things. And of course, these landscapes don't stay the same. They change. 50 years ago, that landscape of London would have been very different 100 years ago. So we want to build on these things. And when we build, we want to know what's underneath us and if it's stable. Okay? So being able to explore a sense in the ground is really important. We can have basements. I learned whilst I was exploring this was that Sydney Opera House is the deepest basement of any building in the world. There's a parking lot that goes down 200 feet. It's as tall as it is, it goes down the other way. Things learned every day. Okay. Of course, they're probably secret military. So that's all very good. So you think we've got this stuff that we've stuck under the ground. We know where it is. We've stuck it there. Maybe. This is a modern map. I don't know if you can read this. This is a utilities map. This is a junction in America. There's a gas station there. All these lines show you where the electricity and the gas pipes and sewage and water and things go. It's all very accurate. All nice dimensions on there. You can find out where exactly all the pipes are. But we have to deal with old things, especially in this country. And a lot of the old maps can go back to 200 years ago. So if you look at an old utilities map, this is the one from about 120 years ago. And you can see it's not as accurate. So the kind of space that this takes up is a kind of a space here. There's one pipe there, possibly. It's not very accurate. And it will say, oh, that pipe's about 10 metres away from that wall. Well, that wall doesn't exist anymore, so we don't know where it is. So it turns out that we only know about 30% of what we stuck under the ground. Okay? So it's a big problem, because how do we find it? At the moment, we just dig lots and lots and lots of holes, trenches. Right? Half of those holes are empty. And the ones we do find, we hit things like fibre optic cables and break them. So this is a problem. The most expensive one was £500,000. They broke one cable. It's £500,000 to fix. Ouch. Okay, so we're going to dig up the roads and we're going to look what's under there and fill back in the holes we didn't mean to make. So that causes congestion, roadworks, and that's a big problem because we get angry. Also, in terms of kind of effects on the economy, it can cost £5 billion a year. Huge amounts of money, so it's quite important to be able to look under the ground. What we'd like to be able to do is just sense what's under the ground, not dig holes. That would be really good, right? That's the idea. Going trenchless is the idea. So how can we look underground? One of the main techniques is ground penetrating radar. It's not a lawnmower, it's ground penetrating. So they probably brought parts from a lawnmower. Okay. And the way this works is like echolocation or from bats or sonar location on submarines. We send a ping down. Right. So we're looking for buried treasure like this. What it does, it sends a ping out, electromagnetic pulse out, reflects off the material we want, comes back. And we record how long it takes to come back to us. Okay, that tells me how deep the thing is. And I do that over lots of different points, and I can build up a map of objects that are far down below. Okay, this is about 10 foot deep on that map there. Okay, so this is the main kind of technique where you can do it's kind of looking for graves here. The tombstones kind of give them away at the top, but this is what the signal actually looks like when it comes before you analyse it. And of course, if you know Time Team, everyone remembers Time Team, Baldrick in it, they always found Roman villas with ground penetrating radar. Okay, there are some other tricks, standard techniques. One's electromagnetic, so we basically take a multimeter, stick it in the soil, and we look at how the electricity flows between 2 points in the soil. Okay, it's quite a standard technique, you get quite nice images. Doesn't quite work when there's concrete though. Right? You've got to put these rods quite deep, so reasonably accurate. Another one is if you're looking for a pipe, you can send signals down the pipe and then you can listen to it electromagnetically. That's one trick. And then you can have metal detectors, or this one's just measuring the change of the magnetic field from the Earth over some kind of ancient stone circle. And if all that fails, you can get out your listening rod. So if you've got a leak, this is still what they do. They go around with a big stick and go, can I hear the leak? Can I hear the leak? Can I hear the leak? Okay. So they're the standard techniques. But there's problems with them. One of them is it's only sensitive to about that depth, 5 to 10 metres. It's not very good. We can't see any of this stuff that's below us. Right? They're all transmissive, so that means we're sending energy into the ground. That dissipates, so if we want to get deeper, it's more energy, and there's only a limit that you can go down to, so say 5 to 10 metres. Depends on the soil. Ground penetrating radar, if you've got nice dry sandy soil, that'll go down 10 metres easy. If you've got wet clay soil, like we have a lot of in the UK, centimetres. That's a big problem. Also with kind of size of objects, if you want to go down deeper, you can only sense really big objects. The signal gets weaker as well. So there's this kind of scale, small size and depth issue as well. And all the other issues like electromagnetic noise and interference from other systems. So can we do any better? Well, I've got the boring end of the talk. I cannot do any better than that. But first I have to address the problem in the room, the white elephant in the room. I don't know if you've all felt it. I've certainly felt it. You're all attracted to me. Yeah? Can you feel that? I can feel it. And more importantly, you're all attracted to each other. So before I close the door, we'll have a loving. Okay. I'm talking gravitationally attracted, so Nick kind of alluded to this earlier. We all have mass, we're all gravitational objects, we've got kind of a gravity field and they attract to each other. So for example, Sadie here, she's immensely attracted to me. It's by the same amount as House of Light on her head. That's about the same amount of force between Sadie and I right at the moment. I had to guess it your way, I'm sorry. There's about that kind of scale, tiny, very small thing, but it's always there, every object has it. So can we use this as our kind of measuring tool? Everything experiences gravity. We saw some equations earlier that said that you've got to have mass to experience gravity, but we also saw some cool things with gravitational lensing. So gravity is also known as being a distortion of space and time. So indirectly, light is affected by gravity. So everything is. Gravity is not constant around the Earth. If you go around the Earth, it kind of changes a little bit, goes a bit increased, decreased everywhere. This is a kind of a weird potato Earth, where it shows that the bits that stick out are, we'll go back, are stronger, and then red, stronger, and the bits that are blue are a bit weaker. So if you want to lose a few pounds, just move over to South India. That'd be a good place. You know, weight is due to gravitational pull, so get a bit weak, a bit lighter there. How do we use this, right? So let's say we're going to do a little exploration under the ground. We've got some very dense material, some buried treasure, some less dense, that's the tree roots, and then we have a big hole, lack of density there, really, no density. And so if I were to measure the gravity as I went over here, you'd find that it would increase a little bit as we went over the dense things, then decrease a little bit more as we went over the tree, then decrease as we've got the void there. There's less gravity. So if we can measure that, that would be really useful. And the important thing with this is that it only depends on mass, or mass density. So the kind of soggy soil or dry soil doesn't really make a difference too much in the experiment. And also, it's passive. You're just measuring that gravity. You know, you can't hide it. It goes all the way down, so you can measure really deep objects. So all those things I showed you earlier, we can measure all of that gravity. Okay. That's some of the ways they were discovered, was with gravity measurements. So, how do you measure gravity? Well, we've all measured gravity at some point. We've dropped a cup. It smashes on the floor. So the speed that it went down the floor, that's the measurement of gravity. Nothing more clever than that. Of course, you have to pick it up again, glue it back together, and throw it off again some other place. It gets a bit dull. So what you do is you stick a weight on a spring, and you let that bounce. So the spring's pulling it up, and gravity's pulling it down. And it'll oscillate back up and down, up and down. And you just measure that frequency, and that tells you what the gravity strength is. And you can buy these things. This Intrex gravity mass on a spring. This is my animation, which took far too long to do. Right. Okay. There's other ways. You can use a laser, drop a mirror, something like that. Just how fast that mirror takes a drop. Measurement of gravity. Okay. You can have really fancy versions of this. You can stick it up in space. This is an amazing tool. This is called the GOCE, G-O-C-E. It's a gravitational and ocean circulation explorer, something along those lines. It's termed the Ferrari of satellites because it's a sexy beast. So it's got radar on it and gravity measurements, and you can do fun things like this is the change in gravity over time due to the ice caps. So it's monitoring things up there at the moment. Okay, and if you're interested, that's what the gravity map of the UK looks like. So the blue spots are the kind of the weaker points. Interesting, there's a blue spot about here on the left, so my hand can't be stripped back. Up here. They discovered this, and there's a kind of weird blue spot there, and that's due to a buried impact crater. Slightly less mass there. It blew everything up. Okay, interesting. However, there's a big problem with gravimetry, just measuring these things, and it's the equivalence principle. Anyone's heard of that? So we could say that on this axis we've got gravity strength, how strong gravity is, and the force that gravity applies into something. And they're linear to each other, they're proportional to each other. That's Newton there explaining that. So, for example, if I want to get a spacecraft off the surface of the Earth, we need a huge amount of force to lift it off. Once you're in space where there's not much gravity, you can merrily float around there forever. This is the same as Newton's laws. Newton's laws at school. Force is proportional to acceleration. Push something harder, it gets faster. Right? Straightforward. Similarly, if I want to accelerate a tennis ball, that's pretty straightforward. Don't apply too much force. If I want to accelerate a tank to the same speed, I require a huge amount of force. It turns out that that force is proportional to acceleration, and the proportionality is due to its mass. It's called its inertial mass. And check with Nick whether that's correct, that his idea of things. Basically, that mass is resisting the motion. So if something's heavier, it's harder to push forward up to that speed, it's resisting. That's kind of equivalent to the fields that he was talking about. And so it happens that the proportionality between this graph is also mass in gravity. That's gravitational mass. I call it gravitational mass, inertial mass. There's no reason why they should be the same at all. Why should the gravity act in the same way that inertial forces act? Okay. Einstein said they're the same thing, and we kind of believe Einstein most of the time. And there are still measurements going on to this day to check those two things are the same. Okay, we still don't believe everything Einstein said. Okay, so if these things are the same, these are two equations. And if we were measuring the same amount of force, we can equate the two together. And masses on both sides. If it's the same type of mass, we can get rid of that, and we're left with gravity, strength, and acceleration. Right? So if in a gravity field, something will be accelerated. It doesn't matter about anything else. It doesn't matter about its mass or anything like that. It just is accelerated. Okay, so Galileo did a famous experiment where he dropped weights off the top of the Leaning Tower of Pisa. And they found that a light weight and a heavy weight, when they fell, landed at the same time. You may have seen Brian Cox do the same thing in a vacuum chamber. Okay? So that's interesting. It doesn't matter about mass, they fall at the same time. But this is a problem. Say I'm in a lift. For some reason, I've been trapped in a lift. There's no windows, right? And I feel a force that's pushing me down here, so I say that's probably gravity. It's pushing me down here. There's no reason why that isn't me on a spacecraft going through space and a rocket pushing me up, right? I cannot tell the difference when I'm in that lift. Okay? That's a big problem. So how does that affect me when I do these measurements? Well, say I'm going along with my lawnmower, my gravity detector, over lumpy ground, and it's vibrating like this. Those vibrations are accelerations, right? So am I measuring changes in gravity, or am I measuring acceleration? I cannot tell. There's no way of telling. So the way they do these measurements is they sit there for an hour in one spot, measuring, and they move spot, measure. But it's not very efficient. It's very expensive at time. Issues. Also, the gravity of you affects these machines. So when they do it, they have to remember exactly where you stood with relative to that machine, so you have the same measurements each time. Okay. Hard experiment to do. Really, really weak. But there's a way around that. Okay, so this is my problem. I can't tell the difference between being in space in a rocket or being near an Earth. Okay, but what if I have a twin who's mysteriously also in the lift in space? Who knows why? On this one on the left, they're joined together, so the force I feel is the same. Right? Nothing interesting there. However, on the right, the chap on the bottom is closer to the Earth, so he feels a bit of a stronger force than the chap on the top. Okay? So if I make two measures, if I subtract one of those from the other, this is just acceleration. Subtract that from that, you get 0. Right? That's gravity. Subtract from that, you get something. Right? So that's change in gravity over space. It's a gradient of gravity. If I can measure the gradient of gravity, I can get rid of all these accelerations. Vibrations don't matter anymore. Okay? So I just have two accelerators and separate them by some distance. And my gradient is just the difference in the two divided by the distance. Right? If I want to make it more sensitive, separate them a bit further. These things exist. They're very, very sensitive. Say the vibration noise is common to both. It's common mode, we call it. Completely cancelled out. However, to do this, those accelerometers have to be identical. And the electronics have to be identical. To 1 part in a billion identical. Okay, that's really hard to do. Real materials, you can't get that kind of accuracy, so it's very difficult to get that kind of accuracy. Also, they have to be in specially damped. Even though they're insensitive to vibration, there are other issues that come into it. This is a real thing. This is the full tensor gradiometer. It's the most developed one. It used to be secret. Top government secret, because they use this to navigate subs. Who's seen Hunt for Red October or read the book? Yeah, something? Okay. in it, he said, well, they use gravity gradients to navigate. That was top secret. He went to jail for saying that in the book. I don't know if people knew that. Yeah, he went to jail for about 3 months. It became declassified in 94. Anyway, the easiest things to measure things. They're very big, they're heavy, they don't work well on land. You have to stick them on a plane, so you have to buy a plane as well if you want one of these. However, they're used to discover very expensive things, like lucrative things like diamonds and oil wells. And so you can nearly predict how well the oil companies are doing by how many companies do gravity and bust. If there's not much money coming out of oil, they go bust, and that's the problem over time. So if you want to, so that's one application, but there's loads of other applications. So I was talking about civil engineering, under the ground. That's too expensive. Archaeologists can't use that. They've barely got any money anyway. So we need to make these things smaller, cheaper, and more robust if we're going to do something useful or expand their usability. So, what's the most sensitive gravity measuring tool that we have? LIGO, the LIGO interferometer. It measures gravity because it's measuring distortions in space-time due to gravitational waves. Okay? And it does that by measuring the length of this arm compared to the length of this arm. And there's Einstein when he came up with the idea of this. He was about my age when he came up with this idea, so I'm a bit late coming up with something genius. But how do these things work? Okay. Light is a wave, oscillates like this. If I have another wave and I come along, oh, sugar. The peaks here line up with the peaks there, and the troughs there line up with the troughs there. So when I add these two together, I get constructive interference. It gets brighter. I do the same thing, but this time I'm going to shift that along so the peaks match up with the troughs. Add those together, boom, nothing. Right? Deconstructive interference. And so I can do a fun thing where I can make an interferometer. So I get a laser, shoots out that way, gets split with a bit of glass here, some of the light goes that way, some of the light goes that way, comes back together, and I measure them on the detector, and I see these dark and light fringes. And what happens is, if I move one of those mirrors a little bit, those fringes will change. So I'm moving this one out, I can measure those fringes going up and down, and that tells me about how much this moves. And that's how LIGO works, essentially. And that's the data that it got from LIGO, these oscillations that came out from it. Okay? I've got a demonstration of one of these. This is a real interferometer, brought from my undergraduate laboratories. And is it still aligned? Or you can press it. So there's a bright spot there, merely sitting there, and you'll see over time that it will get dark. That's the light interfering deconstructively, and it'll come back again. That's just thermal variations of the read. If you clap loudly, you might get it to jump. Not quite. I didn't know if that would work. Oh, that's maybe. Didn't know if it would work. It's on a very vibration damp-proof bench that's designed to not do that. If I just slightly touch that mirror, that jumping boat things. So that's kind of how LIGO is. This one's not very sensitive because it's very small. LIGO is nice and big. Problem is, light does not directly measure gravity. It doesn't have mass. It doesn't directly interact with it. It just interacts with distortions in space, and those are tiny. To give you an idea, LIGO just measures the distance between these mirrors. Okay, these are really, really fancy mirrors. All the effort goes into making these mirrors. That's how sensitive LIGO is. It can measure distance, change in distance that much. It's 18 zeros there. To give you an idea of scale, that's an atom. It's incredibly sensitive. It's absolutely astonishing. That thing, if I do it properly, will be able to measure something about that scale, that size of an atom. If I do it properly. However, LIGO is 4 kilometers long. I can't stick that on a building site, right? They won't let me. So how do we get around that? And this is the gotcha. Quantum mechanics comes back in. There we are. Can't escape it very long. Okay. So how do we do quantum mechanics? Right. So Nick showed this nice picture of an atom. Doesn't look anything like that. An atom. Atoms are fuzzy things. The electrons are probably there. They're probably a bit over there, and they're probably a bit over there. Never distinctly in any one spot. And this is the kind of trick between. This is the kind of theory of quantum mechanics, that we treat everything as kind of this fuzzy, kind of wave-like property. This is a real picture of an atom. That's actually a hydrogen atom, taken only a few years ago. It's all a bit fuzzy, not quite distinct, and that's just the fundamental nature of quantum objects. Who's heard of Schrödinger's cat? Yeah, Schrödinger's grumpy cat. He's grumpy because he got stuck in a box with some poison that was activated by nuclear decay, and someone closed the lid on him, poor thing, and we don't know if he's alive or dead. That's why he's grumpy. And this is the thing about quantum mechanics. In real life, we say, oh, he's either alive or he's dead. But in quantum mechanics, he's both alive and both dead. It's probably both dead, probably alive. Okay. And if it's probably, then it really is. Okay. That's a strange thing. And as Nick said, with this thing called Heisenberg's uncertainty principle, this is one of the subtler effects of this, is that if I know a few things that if I know really well, oops, come back, right? So, for example, energy and time. If I know my energy really well, I lose information in time. Similarly, if I know my time really well, I lose information in energy. This is an aspect because we treat atoms like waves. This is a wave effect. It's actually quite classical. If you're interested, it's Fourier transform of the element. People are interested in that. There's another two, velocity and position. I know my velocity really well, take a snapshot. I lose information in my position, it becomes blurry. When we say it becomes blurry, this probability wave becomes more evident. So what we can do to get to that stage is if we make things very, very slow, near standstill, and by that I mean cold, we start losing information on where they are, and they become more fuzzy, and they act more like waves. Okay? And if we've got a wave, we can make an interferometer. Okay? And that's what we do. If you want to know how we make things cold, you can ask me afterwards. I've got some slides on that. Okay, so what we have is our atom. This is a real thing. This is an atom interferometer that's made by NASA. In comes our atom. I'm going to zap it with lasers. And the laser makes it so the atom is either going possibly one way and possibly the other way. Just like in interferometer arms, they go both ways. And I can do a few more zaps of the lasers and combine them, and now the atom is there or not there. It interferes with itself. This is a single atom interfering with itself in space and time. It sounds weird because it is. Okay? It happens, I promise you, because I've seen it in the lab. That's real data. That's a cloud of atoms, about 1 million atoms in there. The blue and red things are different energy states the atoms are in, and there are points where they completely cancel and they're not there at all. They've disappeared. This is done in the Stanford research labs. They separate a little bit. In my lab, we do a few microns. They separate by. The record is 0.5 meter. So I take a single atom. I have it probably here and probably there, and we meter apart and bring it back together, and they interfere with themselves still. So we think of these things as being small, but real big kind of experiments. You can measure tidal forces with this. So if something changes the distance between those two arms, gravity does this, you get a change in interference pattern, and you can use this to measure gravity. And what's important here is that the measurement is by atoms, and all atoms are absolutely identical. So this problem I said about the fact that you have to make these materials 1 part in a billion identical to get a good measurement. With atoms, given, right? They are absolutely identical. You can't tell the difference between them. They don't wear down, there's no moving parts, they don't drift, so one measurement here is as good as a measurement in a few years' time, and it doesn't have to be recalibrated all the time. And more importantly, they have mass, so they're directly sensitive to gravity. You can also do fun things. You can measure rotation with this. So you can make an atom rotation sensor. Compared to a laser rotation sensor, it is 10 to the 12 times more sensitive. You can do some really cool stuff. However, it's really hard. So it's only still in the lab at the moment. These are very complex machines. What do? I did my PhD making these fun things. So that's a cold atom cloud. That's 10 million atoms cooled down to a millionth of a degree above absolute zero. Coldest stuff in the universe. Nothing naturally that cold. And I made these kind of interferometer measurements. These are all fun. I did this for more fundamental reasons, and it didn't sit well with me. I wanted to do something that made a difference, that came out of the lab, made useful things. So I started making miniaturized versions of the equipment. So I take something that's about this big in my lab, and I make it about the size of a post-it stamp size. That's what I do. I do some microfabrication techniques. And making these small things means I can be part of the UK Quantum Technology Hub, so we're using quantum effects to do new sensors. That's a gravity sensor developed by University of Birmingham, we collaborate with. It's not a gradiometer, so it only does one measurement of acceleration, but that's hard enough to do in itself. And my new research, which has only just started this month, is why I'm doing this talk on this thing, is to make a gradiometer. At the moment, you have to make a very tall one of these, about 2 meters tall. The real ones, they're very big and bulky. They start looking like this big, heavy 1-ton thing you stick on a plane. And I'm looking at ways of making these small, tiny little things, but making lots of them. and combining with optical interferometers to make them even more sensitive and more predictable and cheaper. So you can use them for civil engineering applications. And so to finish off, there's a number of things that we can use it with. You can ask me about any of these and how they might be useful. Ones I'm interested in, metrology. Haven't said it, but these atom interferometers are how atomic clocks work. Exactly the same stuff. Civil engineering is my main interest in. I do like a bit of geology every now and then. Navigation is a really important thing. As I say, this was used for submarine navigation at some point. And that's the end of my talk. Thank you very much. That was really
Are you laughing at that or me? When we ask questions this time, can we have people that haven't asked any questions before, so that everyone gets to sort of say something?
I didn't get any bingos. I'm very curious about this stuff.
Enterprises. Anybody else wants prizes?
So, yeah, questions.
Stunning silence. Oh.
I've got a question about that. Sure. So, gravitational pull, planets orbiting the sun, mass is affected and all that kind of stuff. If we took sort of mining or mass out of a planet, could that affect the gravitational sort of orbit of a planet?
Oh yeah, definitely. So the question is, if you had a planet and you took all the mass out of the centre of it, would it affect the other planets that are orbiting around it? Exactly. The moon is only stuck to us because it's gravitationally attracted because the Earth is so massive, and likewise the moon is massive as well, so they kind of affect each other. So the tides are, of course, the moon affecting the Earth.
So if you mined a planet enough, you basically...
Yeah, if we emptied out the centre of the planet, which I'd be interested to know your plans on doing this, the moon would fly away. So, in fact, we'd probably crash into the moon because it would attract us stronger than we can.
What kind of depth can you penetrate to, and what kind of density differences will you?
So the question is what kind of depth can we get to, and let's do this with gravity. You measure everything that's below you, essentially. So you go all the way down to essentially the Earth. The problem is that's very hard to distinguish all the things you're looking at, and it's actually quite a hard computing problem to work out the objects you're looking at. And there's another issue, is that these things are so sensitive that just the rubble on the surface will act as noise in your detector. So you can do something. So I talked about having 2 measurements. You can have more. And the more measurements you have, the more closer to the surface they're sensitive to. So you can use that to say, I just want to measure this surface, get the data out here, and I can subtract that to give me the information that's underneath it. And you can do these things. That's why I want to have multiple sensors, because I can then tune it to the depth I want to get to. Yep.
You were saying that when you're measuring it, someone's physically doing it, they're affecting the measurements. Why isn't that automated? Why aren't there like trapped vehicles chugging around?
Because poor geologists are very, very poor. Yeah, no, just the material it's made of. You get a thing called self-gravity. So the fact is the gravity is made of metal, tracks itself and affects it, so you can take that to the system. So yeah. And it's cheaper to employ PhD students than it is to Any questions?
Thank you very much. Does everyone want to give a round of applause for